all of you at this very wonderful event, the joint seminar of TÜBİTAK Research Institute of Fundamental Sciences and TÜBİTAK Marmaris Research Center, which will organize basically rely on the unifying feature of science for humanity, which provide us with the power of sharing ideas and understanding. As you know, recent advances in electron microscopy instrumentation and methods have made it great progress in physical and life sciences. This in turn makes possible identifying and challenging addressing new fields in this area. With this in mind, it is our distinct pleasure that we have very special speaker, a world-class expert in the field, as well as a wonderful person, Professor Xiaoqing from the University of California, Irvine. He is going to give a great talk on proving the emergent properties and dynamics of interfaces by electron microscopy. At this point, I want to hand over the word to the Vice President of Marmara Research Center, Dr. Osman Okur, who will introduce our speaker. Please.
Is also natural direct voltage surrounding material surface and quantified voltage sample voltage meter. Subsequent is an intended to recognize metal samples and electron microscopy is final development and verification of normal transmission electron microscopy methods for providing according to platform. Focus of time is behavior of material. This works has led to discoveries of new material and lower controls. Subsequent, the system is a errors and times the assumption is level. These are related thermal protection, analytical particle society, microscope society, analytical, and material society. These published over 400 years papers in highly critical. I want to thank the for the last statement and invite him for the response.
Thank you, Vice President, Dr. Ali, Director Ali. Ladies and gentlemen, good morning. It's my pleasure to have this great opportunity to present our recent work on electron microscopy. This is a new work for me, the first time to visit Turkey, although I have friends who work in Turkey for a number of years, just hard to manage to get here to visit. So finally I'm here. And also we have suffered 3 years pandemic, but now fortunately we are able to have interaction in person. So it's my pleasure to be here and to meet all of you. If you are interested to talk about science after this seminar about the next 2 days. And there are the schedule, so just everyone who's interested in science. All right, so my presentation is entitled Probing Emerging Property and Dynamics of Interface by Electron Microscopy. So I'll first tell where I come from and what is my research interest, and then move on to the specific topic for today's seminar. This is a map of Southern California. UC Irvine is located between San Diego and UCLA. It's closer to the UCLA airport along the west coast. Irvine is a new city, it's a plant, and it's about age at the university, so about 55 years old. And it's one of the 10 UC campus. But you see, each campus operates as independent universities. The University of California, Irvine has is built around this central park. So this quarter is for engineering, that quarter is for science. My appointment is between engineering and science. So I work for interdisciplinary institute called Irvine Material Research Institute, was established along with my move to UC Irvine. So that was part of my job, establish this institute. We use a first of all these important fields which are stable for electron microscopy. Irvine Material Research Institute. The Irvine Material Research Institute consists of a state-of-art material calculation facility, particularly for atomic resolution calculation of materials, the structure, composition, and properties. This is the initiative started from university, and then with a recruiting of the center director, and that was me, ended up with me. And then established this material calculation facility with a whole different facilities organized as an institute. With a common structural analysis for X-ray and other things, and then surface science and transmission electron microscopy, which is completely new since last 5 or 6 years. We also have a new facilities for material calculation, particularly for soft materials and for instrumentation, but organized and accessible by all individuals, both university or also. And then future expanding to quantum materials and energy materials research facilities. This is basically how the facility is being organized. So the facility is organized as a shared facility for all the researchers in material science and engineering, also biological science. And we have 8 PhD level staff scientists who are very well trained experts in each of their expertise area, and also have training staff. We have some unique facility for founders using TM. I will show you through my detailed work to see how the unique functionality of text for this instrumentation. And then this facility is available to everyone who are interested, not only just for UC Irvine, but you see UC Irvine typically we use about 60 to 65% of the TM part, and then other universities around it will use another about 20%, and then about 15% for companies, 10 to 15% for companies. So this is a great resource. The research facility is one part of the Emergent. So another goal of the institute is to establish center of excellence. We are fortunately, through the last few years, we obtained a National Science Foundation's Materials Research Science Engineering Center, which is called MERSEC, which is very competitive to the US, and many universities in the US try to get this center. So we are fortunate to get this center for the first time in the university history. That we got the center with a 2 focus research area. One is the complex concentrated materials, both including metal and ceramic materials. Another is bio-inspired active materials, which is involve chemists, physicists, and chemical engineer, and they study the supermolecular materials, which can be tuned to become interface between bio and real materials. So this is a 2 different focus. And this center involved 18 professors, 17 from UC Irvine and 2 from outside collaborate. They have to work together collaboratively for each these individual 2 topics. So they have to collaborate, and this in the same way. So the measure of the center very straightforward. So people either collaborative and then publish together as co-authors. If you just do a great job, a great work, and just involve in the whole group, and then the center is not successful. So this is my reason for the analysis muscle. But there is an overall picture about carbon material resources too, and also how was organized. The presentation is more focused on the work that have been done in my own research group in the last few years, and particularly for advancement of electron microscopy. The materials studied in my group mostly are thin films and nanostructures built by layer and the actual group method. So my group we have the atomic layer actually by first layer adaptation, and then we consume the group. But we also collaborate with other MD groups and getting this nanostructures materials by thin film groups. So there's only slides I talk about synthesis. So my focus of the presentation will be on the atomic scale and the understanding of the structure of the relationships, particularly in the nanostructure and the surfaces. So in my group, we are focusing on the probing atomic scale structure property and dynamics of interfaces, particularly in the nanostructures. In the science, we are interested in including emerging interfacial phenomena such as atomic scale structure, property, dynamic behaviors, and also the structure of the relationship. This is important to understand the processing and design of the materials, and also how to tolerate real functionality of the materials. The materials of our interest, including quantum materials, particularly for strongly correlated materials, ferroelectric and multi-priority materials, and recently a lot of interest in 2D materials. And that also interested in the energy materials, including single atom catalysts and photovoltaic and batteries. And you will see there's a very important tools for electron microscopy allow us to study the functionality and also the structure and chemistry of the materials. It was an institute here. You see how the structure, microstructure, composition change, topology, and even atomic scale phenomena can be understood with the in situ method. I will show you some example. And this is a new development will be expanded with So now I just focus on more specific topic. First, on the very quickly introduce ferroelectric material. Ferroelectric material is characterized the existence of spontaneous polarization, and which can be switched back and forth by applied electric field. And people know the magnetic material has very close similarity. And ferroelectric, due to this switchable functionality, ferroelectric material can be used as memory devices, which is already a commercial product. This is a one example showing rhodohedral crystal, but still have a cross-sex structure. And this crystal is distorted on the body diagonal direction, so that the correlation with the material becomes polar. This is showing unit-cell symmetry. Can be caught along one of the body diagonal direction, and this will generate different kind of domain structure. Overall, the cross-section material, it will in the cross-section material, you can see three different kind of domain structures with a polarization changing directly by 180 degrees. That's like anti-phase on the steel ferroelectric domain wall. This is a 109 degree polarizing rotation. This is called 109 degree domain wall, or 71 degree change of the polarization direction. This is called 71 degree domain wall. So overall, with this kind of material, you have a three different kind of domain wall type. And this domain wall motion dynamics will determine the property and functionality of the ferroelectric material. This is just the TM image showing how the domain structure looks like in the TM. You see the plan view TM study is just electron beam delivered to this surface, and then all this domain wall will appear as a stripe, this along parallel along the beam direction. And then if you cut the material in this direction, And then electron in traveling on this direction, and then you can see the structure looks like this, and exactly just like that here. So this is a cross section of the same sample, because now it gets 3D view of the domain structure in the ferrite material. So in ferrite material, although it is it has been used in the memory device and many other kind of devices like actuators and sensors and so on, but still have a lot of unknown, unknown phenomena, and also some scientific question, fundamental scientific question was not answered. So this including the origin of electricity and how the domain can reflect and grow, the interaction between the moving domain wall and crystalline defects, interface, and so on. And also the electrochemical condition and boundary condition is critical for the property of ferrite material. All this to answer those kind of questions and require a quantitative resolution imaging of the domain walls and domain engaging process, and to see how we are going to measure and map the spatial distribution of the domains and domain wall, and also the normal states of the correlation. If you change local boundary condition, the correlation state will change. These are new fields need to be explored. The exploration of the atomic scale property of ferrite has been going on for decades. I just want to highlight a few things that we did earlier when I was reading. So that time, and then the atomic scale measurement of correlation is not available. So we developed that using quantitative TM methods. At that time, there's no emerging drug TM, but we can use a quantitative method involve atomic structure simulation, image simulation, and then to model the system, and then get precise position of each element in the crystalline materials using the coordinates determined by quantitative TM. And then we can determine the center of the positive charge and center of negative charge. And then we will know the type of movement for where it is. And that this is a way to determine the correlation and by determining the type of movement from unit cell to unit cell. This was done by early students. And so this is about around 2000 to 2002. And then the next generation student, Chris Nelson, and he further developed this method by using operating current TM. The TM was the very powerful team microscope located in Irvine National Lab. And this was a US Department of Energy graduate program. So we start very stable high resolution microscope at that time, using the technique developed by WK. And Chris was able to develop a tool to automatically map the type of movement from unit cell to unit cell, so that you can use this method to discover the unknown phenomenon. This is just a cross-section image of ferrite. This was ferrite growing on the turbid standard, which is an insulator but has similar crystalline structure as the EFO. So this interface is covariant. So the ferrite grown insulator may have a multiple domain structure. Then the combination of the domain, this straight boundary is a domain wall. The correlation will change from here to here to here. It's just changed by 190-degree rotation. But you can see that it's a very interesting phenomenon. If you look at this domain wall today, it's very straight, nothing special. But this domain wall is straight, and then you have this dark region, bright dark region. This is a triangle like here. Now you look at along this straight terminating triangle domain, straight terminating triangle domain, and there's no exception. Then it's in our eyes. And this looks. There must be something wrong in physics to try to understand this. Now, if you look at this small region, including two perpendicular vertical domains combination, one with defect, one without defect, and then enlarge this, just put the high magnification to see a atomic resolution image from that region. just look at it, you don't see much. But if you use the method developed by Chris and William, you can see the dipole moment from each unit cell. Now you see the polarization is changing from this direction to that direction. It's like a vertical, like a 90-degree rotation. But remember, polarization is not exactly in plane. It's about 45 degrees away. So that's the angle in 3 dimensions is 109 degrees. So this is 109 degree moment wall, and this part set just up and down, right? This and that 2 domain wall just very similar. Both are 109, just the opposite rotation. But this here, this reading is quite interesting. It's in polarization follow the arrow. Go up, gradually turn, and then to down, and then to the left. This is called closure of it. This also the similar pattern exists in magnetic system. So what is the reason for this? And then very straightforward from simple physics perspective, we can get this kind of picture. So polarization, the direction material is, we have a bond charge. So it starts with negative charge, positive charge with the other hand, and then line up. So when this moment accumulate at the surface or interface, you have a negative charge on this side, positive charge on the top side. So this charge is called bond charge. So it doesn't move itself, it's bonded to the structure. And then the polarization pointing downward, you have a positive charge here, negative charge there. But if you look at this accumulating point of the domain wall, this one and that one, then you see interesting thing happen. This bond charge at the surface and change the sign at the terminating point of this domain wall. And then there's an internal field created by this bond charge that is pointing to the left. But this side is pointing to the right. And then this internal field will influence the orientation of the dipole moment in each unit cell. So that means the field is parallel to the projection of dipole moment as called along the left. But here, the projection of dipole moment is pointing to the left, but the bond charge induced field is pointing to the right. Therefore, these dipole moments will not be very stable if this field exists. Therefore, it will change its orientation very from very interesting closure objects. So this is the origin. And after this was observed, many people in the parallel to research fields are interested to create, manipulate this kind of closure problems. This is 2 examples. One is from Institute Material Research Institute in Chinese Academy of Science, and they found this kind of vortex, anti-vortices in the superlattice of strongly partnered and may partnered. So this is very similar to the closure problem we have seen before. And also, my student Chris Nelson, when he finished, he developed this method for banking, and then joined Berkeley for school, and then continued to study and found this very nice vortex antibodies and vortex antibodies already in the very part of the thin layer with the superlattice to the structural part. You just be not in the same. Well, after this, there's a lot of colors, spherules, and edge of domains, and we can kind of narrow structure, narrow scale color states was discovered. This topic actually today is very active, so far. The narrow scale color regions, color states, or topological state, very actually commodities, So far, I expect what happened in the atomic scale and keenly determine the polarization in the nanoscale, in the unit cell scale, and how to map the polarization change to the 3 dimension. And then this will now provide a way to discuss nanoscale phenomena such as closure domains, voltage, anti-voltage arrays, and so on. And another question I mentioned earlier, and how the paraelectric domains nucleate when you apply electric field or change apply a driving force. And what is the dynamics? This question is very interesting and raised several decades ago. When I was in graduate school, it's in my hair, the days how long in past. So this is my master thesis and study the ferroelectric material and see the ferroelectric mineral. I think this is the first direct observation of ferroelectric minerals. Most exciting is that every form of mineral terminates at 1.4 from a vortices. Okay, and then this structure will change when heating the sample in the transition temperature. And then after I moved to Germany for continuing my PhD thesis, and then working on another ferroelectric material, which is a dancing green chloride with a Professor only. And then you can see that there's a two domain wall and which are very close to each other from pair. And then if three pairs can join together on vortices, these vortices will change its configuration when you change the temperature. Change the temperature, you have a temperature gradient. Temperature gradient is driving force that push the domain wall and vortices move. And then this is the reason why I present for my computer, because this video doesn't play. If you video play, these triangle domains will move the vortex, it will move from here to here when the temperature gets higher and higher. Okay, so that was yeah, the video is not video. So and then my professor asked me, just like a ferromagnetic field, if you apply a magnetic field and then you can speak the wind will move, you do the ferro. This was raised, question was raised 35 years ago, 30 years ago. So and then I said, well, maybe, but we tried, but you see that 30 years ago, the technique is not advanced. It's very hard to do this. So it was not possible. All right. So and then I keep this in mind when I become professor at Michigan and still want to solve this problem. And then one of the graduate students and was committed, Chris Nelson. We started with a conventional prototype with scanning from in the TM. And then it by bias. And then the system looks good and promising, but it's really not designed for this type of work. And then you have the development technique, and then there's a lot of components we designed. This we make a new order, which has become very stable and this is new product. And then which allow you to apply bias from to the point of interest. And then you can see atomic scale action. Because all the video are not directly cannot see motion. But basically, this code will allow you to apply electric fields locally, and then you can see the atomic scale motion is very stable and then the atomic energy. You can also measure the local electrical properties like a CV IV curve from local region that you are interested in. Then you see this can be measured directly. These become quite useful. Thank you very much. So, okay, now this is good. You see, this is the first in situ switching of ferroelectric materials. This is the STM tip. This is the photoreactors. It's also oxide. structurally match very well with substrate and the ferroelectric TBAE. So you can see that when the electric fields applied up, positive and down, negative, up and down. You can see the equation start from the here, the field is strongest, and then might propagate further. And then this just like how the memory device, ferroelectric memory device works. Okay, by tracking the volume of the view domain switch, you can see the ferroelectric hysteresis loop in the obtained with the institute video here. And then with a target resolution imaging, you can determine polarization, and you can see which of the domains dissipating. And most importantly, when the domain nucleated here, and then when this dark reading starts to extend, that means the domain wall is moving. And they can track it. There's a dark point here, that is a dislocation. You can see how the dislocation affects the motion of the domain wall. That can be explained here. So this is dislocation, the domain nucleated, the domain wall moving to here. You can see let me slow down here, but we need to analyze to get information. So then you can track how the domain is moved to the vertical direction, that is velocity measured here, or the domain wall, the motion along the horizontal direction, the velocity is there here. You can see that domain wall motion, getting slower and slower because the field is getting because it's moving away from the strong field region, and then slow down. And then eventually, it is almost not moving for a while. And then suddenly become very high speed again. The reason for this is that when domain move to here, domain wall move to here, this dislocation, holding the domain wall, and just like a barrier. And then when the electric field increase further, the driving force become higher and higher. Eventually, the peeling effect of dislocation will disappear, overcome the barrier, and then move further and suddenly move very fast and then slow down. So this is the first demonstration of the peeling and peeling of dislocated domain wall by defects. All right. So that demonstrates dynamics can be studied in the in-situ electron microscopy. And in ferroelectric material, because it's similar to ferromagnetic material, you always, if there's a no charge balance, and then the ferroelectric material will try to break down to form multiple domain structures like this. But if you look at the termination, as I mentioned in the previous example, bond charge. The bond charge at the interface with insulator will be very important because the bond charge has increased energy. With the system, have some free carrier, and then the free carrier with opposite side of charge will be trapped at the interface. And then the trapped charge cannot leave from interface, but can move around the interface. This will form the two-dimensional carriers gas. If electrons trapped to compensate the bond charge, positive bond charge, you have two electron gas. If holes trapped to compensate the negative bond charge, you have a whole gas. This is just theory, just by look at the interface. And this is also predicted by theoretical calculation. But for a long time, there's no direct measurement. Measurement was available, but it's also insulated that no electron gas in ferroelectric interface at all. So what is this? Well, why? Now, how can we understand this? So this is our in-situ experiment, and show the sign to the new interface between ferroelectric and insulator is conductive. So this is a very well known about previous example, right? Switching this is like a very small tip. The field is from here, and then first nucleate and then move further. There's a rejection only. And then this is another sample, very similar to the first one. You have an insulator. This is a 2 yards now. Other the conducting outside of the bottom electrode. This is ferroelectric. This is another insulator. It's functioning positive. So this structure is similar to that, except a additional thin STO. And then you apply electric field on the top of the STO across this PZT. And then you see the important things happen. When the electric field increase, nothing happens. Still have a monodomain, single monodomain structure. When the field increase further, then you see this region will switch along the whole film and suddenly become bright. You'll see that in a second. I think it is there. You saw that happen.
Yeah.
So and then these things we just worried if I do it again. So okay, so this is switching at one time, just like a capacitor. This means that there's a bottom electrode with you, and then must be a top electrode, but we did not intentionally make top electrode because STO is supposed to be insulated. This indicates that either STO is conductive or the STO ferroelectric interface is conductive. To rule out STO is conduction itself is conductive. We just prove different STO layer with different thickness. If the conductivity is switchable, it is a scalable, and then STO is conductive. So we did that. We have many different STO thickness and all with the same conductivity, so not scalable. And then the concluding interface is conductive. That's good. But we further ask question, if the electrical carrier at this conductive interface is a ferromagnetic orbit or not. And then we design two experiments collaborate with annual refraction spectroscopy. We determine the interface is conducting and also ferromagnetic orbit. And another signal is a high resolution remote experiment, also confirm interfaces conducting the carrier is magnetic orbit. So that means we have two electron gas with a magnetic orbit. So it's spin polarized electron gas at the interface. But the question is why so many studies in the ferroelectric structure already show that the interface between ferroelectric and insulated is insulated. The reason is that the film, the bulk material people measure always include different kind of domain walls. So for this kind of domain wall, you have a conducting electron gas. But then if you have a 90-degree domain wall, correlating is a parallel to the interface. There's no bound charge at interface or surface. Therefore, there's no two electron gas or 2D4 gas exists. And then if you're correlating up and down, and then at the bottom or at interface, you've got electron gas and 4 gas alternating. And the junction from PN junction that block the current. Therefore, the microscopic measurement of ferroelectric material interface that's always shows insulated, not conductive. So that was on the question. And then we did a similar study on another ferroelectric material. My student, he was trained in TM, and he was also interested in very interesting capacity of scanning flow. You can do piezo force imaging to see the domain structure. You can do conducting electron study to measure the conductivity at interface directly. He said, I can study the same sample in my cross-sectioning TM, and then use a cross-sectioning TM sample to measure the functionality. I thought that was difficult, but he managed to be able to do this. Just quickly introduce the data. That's really exciting. So this is a physical chloride ferroelectric during on 13 standards. We just need a little bit substrate insulator. And then the interface you can see is a very conductive. This is a high intensity. Dark is high intensity conductive. And then the conductivity also changes from one domain to another domain. You can see it's alternating. And then this is shown by the profile, the line profile. So why the conductivity? Conducting is okay. From physics example, we understand the ferroelectric interface to be conductive. But alternating is also understandable by PN junction. So when the polarization is pointing downwards, and then you have an electron gas, and then pointing outwards, then you have a whole gas. And then there's a whole electron conducting region connect to each other. You will form PN junction alternate one to another. So this will be the display here. So physics behind this. We have an Afghani symbol from the University of Nebraska. He was the person with the first principal calculation predicting the ferroelectric insulated interface is conducted either from two electron gas or to the whole gas. But all the microscopic measurement is against that. Okay, and then we talk about our data to feel really excited, and then you do an additional calculation. And using field soup cells and with a different thickness of ferroelectric bismuth product. The conclusion is that the ferroelectric bismuth product is thicker than 8 millicells. And then the band bending at the interface will make the interface either p-type or n-type. And then electrons or hole will be trapped. This will depend on polarization pointing toward interface or away from interface. Okay, this was from alternating in a conducting material. This explains why we measure the conductivity across the domain stripe is insulated because here just a series reaction. But we measure along the stripe, it is all conductive. So that was very interesting on observe. So this is just some of the conductivity of two different kinds of ferroelectric interfaces. Explain why in the microscope measurement we are insulating, but in the nano scale it is conductive. Okay, so this give you address another question. Yes, so the charge at the interface is very important to directly see this kind of electronic charge at the interface. And also in the polarization measurement, the quantitative method that we developed to measure the dipole moment from unicell to unicell, we only use ionic displacement because we have logic consider atomic electronic charge. So the polarization referred to should consist of both ionic displacement and also electronic displacement. Any neutral atoms put in the electric field will have induced electrical polarization, electronic polarization. So they should be considered. So to do this, we have to measure the local electric field, right? Including both ionic and electronic. So can we image the total electrical charge density? Actually, experimental technique is there, but not for atomic resolution. X-ray methods is very well, but it is a macroscopic sample average. Electron beam, converging beam electron refraction has been developed for decades, and they also offer the technique to measure, to determine charge density, but use the fitting of structure that can get very nice as the measurement of the dense charge density. But it's again, this is a space average method. It depends on how big the crop size is. For this kind of CBD, and then the crop size typically the huge size not the atomic scale. Right. So that was motivation for us developing the charge density map in the interface and local structures. We were stimulated by Peter's work. It was very simple, straightforward way to explain electron beam and crystal materials interaction. So the electron pass through focused electron beam pass through the spacer, and then spacer electron beam will lose some will change momentum. The momentum change is directly linked with the crystal field. Electron pass through the spacer. The local field is proportional to the change in momentum. So with this, we did expect that when electron drop and is passed through the sample, will sense the nuclear charge, and this charge, this field due to the charge is to the left, and then the electron diffraction pattern, the center of the mass of the diffraction pattern will move to the right because of attraction. If you move the beam from left side to the right side, and then this displacement of the center mass will be opposite. So this is just perspective, right? So in order to do this, and then we'll do simulation and see if this is true. So this is a Chris Diego PhD student. We did calculation and then simulate the converging the electron destruction pattern when the beam is scanning through the crystalline material very slowly. So each point is a one diffraction pattern. We call this as a 4D scan because the 4D two-dimensional scan, you have a 2D data. Each standpoint, you have a one diffraction pattern that is also 2D data. So total is a 4D, we call 4D stack. So with the simulated diffraction pattern in 4D, and then you can calculate the chart, the field. The field is proportional to the momentum change. And momentum is determined by the set of mass displacement. Okay. So this electric field from the 4D stand, you can see that for strong target, you have a cubic symmetry. It's all like a radial symmetry. This is good. With this field determined, and then you can get a chart information that will just come into on the next slide. But there's a question: in which kind of scenario this interpretation will be valid? In other words, what is the limitation of linearity? So we did a detailed analysis. It turns out when the sample is big enough, for this particular example, sample has to be 5 nanometer or thinner near the linearity. So I'm just not with the detail, so that we know when these methods will be valid. So with electric field determined, and then you can using the Gauss law and then you determine the chart. I will show you in the future slide. So the way this is, tell you how the 4D set can be done. This is a movie done by Colin. It's a directly simply showing the how 4D set will work. The electron beam will scan through the specimen, and then will at each standpoint, you get diffraction pattern. This is a converging diffraction pattern. You collect this data. This is a 4D data, right? And then you analyze this data. You will be able to get the momentum change, and then get the electric field. So there's the method is now we think quite confident may work. Now we want to expand. This is a 4D data. For each data diffraction pattern, we just calculate totally intensity. This is similar to those people who RT and Acosta, this is a hot image, right? But the 4D data we have, each data point is a diffraction pattern. We will analyze the center of the mass displacement. We'll get field. This is the field. With the field, and then we can determine charge distribution. So this divergence of the field, you'll get charge. This is actual charge distribution. This charge is total charge, electronic charge, and also nuclear charge. And this will determine the local potential in the first slide here. All right. With this method, we demonstrate the charge density method for 2 different materials. One is strong target, which is a prototype for the outside. A similar structure, but different kind of parametric property. This is no parametric. It's a symmetric. This is no surprising, very nice symmetric field distribution. But for parametric, bismuth boron, the polarity, as I mentioned earlier, polarity is around body diagonal direction. You can see that this polarity is very clearly demonstrated in the field method. Now, if you go further, divergence of field chart tell you the charge density. This is the charge density of strong positive. You can see the electrons, which is a negative charge with a red color, is uniformly around each atomic column. So this is good. This is a pure crystal. But for the far electron, which is polarized, so now you can see the electron charge is no longer uniform around the column. And then it is on a bridge between the ions. This is very important to form the bonding. And also, original productivity in bismuth chloride is related to bismuth, 6f electron is a non-pair. So this will give you a lot of information, but I'm not going to talk about that details, and still in the early stage. But let's just compare the experimentally obtained charge density in these two different computers. One is ferroelectric, another is not. With the first principle calculation things. DFT can also get charge density, and for both these two materials, you can see for strong metal that match very well. For ferroelectric material, this is fluoride. You can see it's quite similar, but there's some details are not exactly set. So which is correct? So actually, I don't know. So I asked my collaborator, who is a DFT expert. He said, I do not tend to say DFT is more accurate because DFT potential still needs to be optimized. So that's why there's a lot of active work in machine learning optimization of the electrical potential. So we will answer this question later in the future. So, but this is very encouraging. So the density, charge density can be mapped by using experimental method. This applies to small nanostructures, also interfaces locally. So by knowing the charge density, and then you can use it to determine the center of negative charge, center of positive charge, and this including ionic and electronic contribution. With this, you can determine the dipole moment for each unit cell of this material. This match very well with the bulk value in the business problem. Okay. Now we have charge density distribution, and DFT people also calculate charge density distribution. From their data, they develop so-called the better charge analysis. You can analyze using the charge density distribution to analyze many properties, including bounding characteristic, valence states of each individual element, and so on. You can do the same for the experimental data. Just to use example, okay, this is one of the this also probably the same paper we have this addition as an application example. We are strongly taught that it was integrated. This method is ferroelectric. And therefore, interface are very much can be with sharp interface. This is the hardware field. This is the charge electric field. This is charge distribution. By analyzing charge distribution, we can directly see the existence of electron two electron gas. Okay, because the polarization is pointing to the interface. And additional analysis by looking at the position of each airline's anions and also electronic charge distribution, you can see that the change of structure is much faster than change of the electric property. The polarization will penetrate to the non-ferroelectric material as to the but the structure distortion is quite sharp. That is only 2 unit cell or 3 unit cell thick, but the polarization and change will across about 5 or 6 unit cell double. So this is one example. So with the technique we develop, there can be many other things. Another big example is our very recent paper, and we use a 4D step to determine the charge distribution and field distribution around the polar spinning. And this is a very nice example to how the polar spinning looks like. And this polar spinning is switchable by applied electric field. If you are interested in this, then you check that. This is not the box of the talk. So this is a quick summary of what we see by in situ TM by 4D STEM. We can get the dynamic process, we study the dynamic phenomena, and also the local charge distribution and the understanding the electronic property in another scale. But if I have 5 more minutes, I will just touch another area I plan to talk about. So with electron microscopy technique, actually with advancement in electron microscopy, both for operating corrector and monochromate, plus the direct electron detector today, we can have high spectral resolution. We can have very small probe for the scanning transmitting electron microscope because scan. And we can also build very improved energy the analyzer to analyze small energy change in the electron beam. So we got use electron energy loss such as Xiaoqing. With this, we can study the dynamics of lattice vibration or falling for the individual defects, which is not possible. But I'm just not going to cover the detail of use this. I just want to mention that as the device in the electronic industry continually minimize until 2 nanometer scale. And then the local heating, it is important. And then another important is a thermal barrier coating. You know, when you don't want to heat transport to the inside of the device, even for the heat engine, right? You will drop it. So to understanding the heat transport in the interface is important. But the theory about the thermal transport are developed from using computing theory. It doesn't work in analysis. And also people working on the thermoelectrics know that there's many engineering methods to improve the functionality of the thermoelectric field. By introduce interfaces scaffolding. By introducing nanostructures will have lattice effects, and then also scaffolding. Or atomic scale error. This is a multiple element to substitute the individual species. And then all these three different mechanisms, there are different mechanisms and it's supposed to scaffold in different ways. But this is all just from physics perspective. There's a theoretical study, but how do we know it follow scattering in this scale, and how heat is transported in this nano scale, in the atomic scale? Some experimental methods already show that when boundary conductivity in diamond is much lower than foam, right? So this is a rule is low conductivity, no thermal conductivity at the boundary. Also, the interface, like silicon genetic interface, is a model system, shows that the interface between silicon genetic scaffolding and then low conductivity, thermal conductivity, right? But there's no direct mechanism, local mechanism. So electron microscopy developed. In addition to image, you can also analyze the functionality by using EOS. So EOS can be done in different ways. So EOS scattered by the valence electrons, the co-electrons, that were in the ionization energy. You can study the existence of the element in the material without co-loss use. The electron can be scattered by the valence electrons, and then this will allow you to study the electronic property like a band and any kind of related to the valence electrons. Or electrons scattered by nuclei, and then nuclei vibration, that is like a vibration of lattice or photon. This involves very small energy change in electron beam, but now with a new technique developed, there's a very small change, like a few milli-electron volts can be detected. Traditional TEM can only detect energy change with 100 milli-electron volts or higher. These are monochromatic TEM. But there is a non-magnetic extent, you can study very small energy change. So this is one of the instruments in our lab, which is quite unique. At 330 kV operating voltage, we can get a 4 billion energy resolution. This is a very important development. So with the EOS method, we can study the diffraction of electron in the scattering TM. So with a large converging angle, all the diffraction bits are overlapped. There's no distinguishing between different angles. However, if you reduce the converging angle, you see many different spots. Each of these diffraction spots will tell you the scattering to the particular length. And then if you can analyze electrons scattered to different angles, and then you will see the angle result, the scattering of the electron beam by lattice vibration. In other words, you can measure dispersion curve of photon in the from local region. Okay, So this is just a drawing of the Fourier zone. There's a first Fourier zone, and then you have the other Fourier zone. But most important that if you have a large angle resolution, and then you can make many data points, and then to do the formal dispersion analysis similar to the future. So this is the example showing Sonaka and he did real work a few years ago. This is the structure collected use huge amount of time. Each structure will take about 10 to 20 milliseconds, and then this is millions of structure put together and take very long. But this is demonstrated principle. But now with the view detector, then use a much shorter time. With a direct electron detector with a 6 aperture, and they can get these there's a few minutes and quite big improvement. On the demonstrated technique that we are further developed. So by using this EOS vibrational EOS method, we can study the following characteristics at individual effect. This is just a single stacking fault in silicon carbide with 3 Cs, cubic silicon carbide. You see, this is one crystal, another crystal, you have one shape. This is stacking fault. By using the leading range converging angle, we get a sample solution. And then we study the functional analytical spectrum from the interface, from the defect, and from both. You can see they are different. And it will be much easier to understand using imaging. You can see that this is the, you think about to take about 90 degrees to match this. So this is a position, this is a position, here's the interface, okay? This interface is here, it's stacking point, okay? And then this is an allergy. The color indicates the intensity, how many photons with a dark energy. Okay, you can see that at the stacking point, this TN mode is appear as a new mode. And then the existing TN mode, LN mode in the silicon carbide is significantly suppressed in this region from the new mode. That means there's a new amount of new photon exists at the interface. That's a single stacking point. And then we also analyze details. What is energy shift and what is what. But to demonstrate the mechanism, I just want to use this theoretical observation by Professor Wu and build the model with a silicon carbide. This is a single stacking point. You can see here atomic scattering in this stacking point region. Amplitude, and also the angle of bounding are different from the bulk. And then there's a new mode at the stacking point to form. And this new mode contributes to the EOS, the density states of phonon. That's why we see the new phonon modes and also the change of the phonon energy in the world across the interface. Right. That was a great example for the single clarity effect. What about the nanostructure? A typical nanostructure, if you choose an example, would be a quantum dot because it is very well engineered. And then we choose silicon germanium single quantum dot, and then quantum dots shoot from superlattice, the just a continuous chaotic flow. And then each quantum dot will just like a donut. Notice that there are two kind of interfaces around each quantum dot. The bottom interface very sharp, it is extracted very sharp. The top interface is a glory, which is diffuse. The composition of silicon germanium ratio is changing gradually across the interface, across this interface, but abruptly along that interface. This is demonstrated here. This also shows there's a new phonon mode and mode, the optical modes of silicon and have a chip, and this is similar to the silicon carbide. But most important, I will see that the energy shift of the anode mode is consistent with the change of silicon germanium ratio. That means if you change the chemistry, you change the energy of the phonon. Okay, that is straightforward because of mass, right? Okay, that is not surprising. So what is surprised us is that the phonon population indicated by the density of the yield structure. So the phonon population you see from this is a profile across the phonon belt. So this is a one interface. This is another interface. It shows a little bit enhancement at this interface. That's top, diffuse interface, a little bit enhancement, but usually enhancement at this interface. So we try to understand why. That means you have more phonons on the side of each interface. But the enhancement at different degree with two different types of interface. So we try to understand this, and then we think about very simple model. Electrons will be able to measure phonons, but electron is high energy, which also be able to create phonons because there's a giving boost of energy to magnetics and they generate new vibration. So if a vibrational wave generated in the crystal, something and then you have two quantum dots beside it, and then this vibrational wave will reflect upward, and then see this direct sharp interface. And then this sharp interface is get electrons and then coherent, and then a more wave the response effect of refraction, like a spectacular refraction. This is a diffuse interface. It's not like work as like a mirror, but still have a bit of refraction, but not very strong. It's more diffuse spectrum. Therefore, some phonons still affect bounce back, but to this extent. But therefore, the phonon population here will be higher than background. Here also much higher than the background. Therefore, this explains why we have two different enhancement. In other words, phonon will be scattered by interface depending on the sharpness composition of the interface. Okay, this was a good idea. We think about the interface data. We will talk this to the expert of nano thermal transport, Professor John Chen at Penn State. Is a leader of this nanoscale transport research. And then he built models and then to see whether or not to get the result for simulation. It turns out that worked very well with our intuitive model, and then to support the refraction of phonon depending on the sharpness and composition of the interface. And that is great. Now, if this is proved by model, but can we directly measure the direction of phonon propagation? In other words, can we measure the momentum direction of the phonon? So this is another method we developed in this work, and probably the same paper. So we just measure a phonon with two different kind of cube, the momentum of phonon. One is a clock, another is a magnet. And then have a two map of 10 and then subtract from each other. This is called differential mapping. The differential mapping will tell you what is the net direction of phonon change, right? Phonon can go this way or down, but net, this differential value will tell you how many net phonons could get along particular directions. This also indicates that in which direction the heat will flow, right? So this, is indicated that you can get this phonon heat, which basically is flowing from top to the bottom, but not to the reverse speed. Okay, you have the assumption. So this method can be applied to many other examples. This is an ongoing unpublished work. We can apply this to ferroelectric insulated interface. In the earliest part, I mentioned that it's a 2D electron gas. This is conducting electron conductive interface. This conducting interface is very interesting. The phonon compared to the conducting interface will be unfair. It's just not metallic material. It's a spectacular refraction. So this means that the two electron gas at this interface from a region which is conductive and also thermally cooled. Okay. So you can also imagine that if you have a two electron 2D material like silicon germanium silicon and put a piece of graphite with some different in this added structure. And graphite will maybe keep the interface cooler. I just talked to a few people actually a few weeks ago and who did this kind of study, and still quite very excited with one experiment for a single layer of graphite between two different inorganic materials working out. All right. I think that is long enough, and I want to summarize today's talk just by saying that with electron microscopy, you can choose a technique that you solve different problems. For example, you can determine atomic scale property, for example, correlation by using quantitative electron microscopy to see a dynamic evolution of microstructure, for example, the function and the growth of parametric orbits by institute here. And you can also use a new technique of 4D STEM, determining local electric field and the charge distribution, and they get much more functionality from local region. Use a newly developed quadratic electron microscopy. You can determine local global transport and also the vibration of lattice or vibrating molecules in the nanoscale. So this can be very powerful. Look in the future. In addition to those continuing developing of new techniques, for example, we are working on a project to try to introduce terahertz laser with a few poles. One is a pumping, another is a delay and a delay. And then into the microscope, and then put this post laser beam on the sample, and then electron focused electron beam pass through, and then we can study the interaction between electrons and photon and how this respond to this short pulse of the terahertz laser. And then we can use other techniques to improve the sensitivity and so on. Before I stop, I just mention that the work for charge density mapping and the institute here was done by Chris and Diego, graduate student and postdoc with PayPal, and also a student who just graduated a 4-year fellowship. And then the vibrational microscope mainly driven by two people. One is a postdoc, Qing Xu, another is a Czech graduate student. We have been done excellent work in this field. So the work was supported by the Department of Energy and also partially by US Department of Material Research. Our wonderful collaborators, for example, they are strong and Leopold making a very nice interference to us. And Professor Ruchi will provide a select support for the DFD populations. Thank you very much for your attention.
Oh yes, I'm inactivated from Savant University and as well as the base locally here part-time. So I'm wondering about the charge sensing technology. So I'm just wondering how precise can it be? I'm curious. The reason I'm asking is, for instance, there are cases in topological insulators and around in which a vortex or some sort of a localized magnetic field or a small basic magnetic defect can actually capture a fractional charge. So I'm wondering if you can use your technology to actually integrate over this charge distribution and actually tell that there is a fractional charge rather than integer, not integer. Would that be a possibility, or is it like
that very different? So I guess at this point it's very hard to there's the accuracy and also we estimate the error deviation of the data. I think it's still large, very hard to. It's a very interesting problem. It depends on the further development. If we can further reduce the crop size to currently is to 5.5 angstrom. So further improvement by 50% will significantly improve the accuracy. With the current setting, I don't think we can comfortably say we can distinguish fractional charge. But in the future, it is possible. Yeah. Yes.
Xiaoqing, wasn't your electron or whole gas model at the interface for stepwise jumps and domain by domain as domain or motion is annihilated or created? Because that is a really rapid. I don't even think catch it, but then
Giving electron charge distribution as a function of domain motion.
right, you have these electron and whole gases at the
Yeah,
bottom.
yeah.
And at the top, when you actually modify your top, this called electrode and then bottom electrode or substrate. So wouldn't that pose as the domain will move, instead of a smooth motion, a jump like one?
Oh, okay. Okay. So this is not, related to the measurements of the charge, but it's whether or not this interface of charge is a electron gas or whole gas, whether or not this building fields at interface influence the motion of the domain. Yes, it is. So in the details of this PTD switching, business polarized switching, I think there's several paper, visual communication, and also community vehicle was in science paper. By Chris and Gao from my group, described several examples. The building potential due to the interface charge will make one type of domain switch motion is impossible. So have a polarization hint to what particular direction, and the switching have to be kind of a curve, but at much larger field. It is, and also even defects. You have a planet defect, which is also charged. There's also have a building field there, and you have a very much stronger healing effect than shown by the visualization. Yes, very good question. Yeah, it is. It is significantly influence the switching and the growth of the nodes. Yes.
Identity from something in your study. I'm wondering, in this ferroelectric transition, is there a phase transition between the reversals to other phases? Or is there just a small change in the atomic coordinates?
With a mechanism, what is changed in structure when the domain switch? Right?
Yeah.
Yeah. So the contrast you see from contrast between two different domains, you see the middle moving. The contrast is due to the diffraction contrast, because you adopt the diffraction contrast. Electron diffraction is sensitive to any small change in the crystalline structure. For the bismuth chloride example, the ferroelectric domain wall, it is also ferroelastic. In other words, it's like a twinning structure. For electron beam, have from one domain to another domain, the orientation is changed a little bit. Therefore, the intensity of the electrons will be changed in dark field. But for 180-degree domain wall, we do not have a ferroelasticity, only in like a similar to the interface boundary. But the polar material has a low center of symmetry. Therefore, the electron diffraction intensity is different from C or minus C. So that small difference also induce the contrast in the diffraction of image. Okay.
My name is Emergent from TÜBİTAK Marmara Research Center. My question about experimental part actually. I was wondering if there is any special substrate or sample preparation method because I am also working on perovskite materials. We are doing perovskite devices, they by you know, IQ and other electron injection layers and so on and so on. Is it possible to make this kind of imaging directly from those samples?
So, what was your? Just about your material. Your material is you say it's also perovskite.
Correct, I did.
But it's like hybrid perovskite for solar cells.
Solar cell, yes.
The same technique may be applicable to those being sensitive. The challenge is electron being damaged. So in this material I show you, the oxide is quite stable. So the experiment for 4D STEM will cost about an hour to collect all data. For the beam sensitive material, probably only survive for a few seconds or a minute. That is significantly shorter. But there is a very active research right now developing the beam sensitive materials for 4D STEM. Those from Europe and US. So like the diamond thickness, the electron being single results to the UK. And also they are leading to develop the 4D STEM technique for beam sensitive material. That would be available to try. And they also develop the same technique to protect us. It is challenging problem. I think that you see the development of TM in the last 10 years. It's so fast. I think we'll solve the problem in the future.
Thank you.
I was going to talk also later during dinners and stuff, so I don't want to explain it for I like.
The first one. The sample version.
Apologize for the delay.